I am recording now for those of you who want to watch it later, if anybody does. Uh, so just a reminder that this is the probability of K successes in N trials. Again, you should, I don't want to tell you you need to have this memorized, but it's not hard to memorize, and it will make doing problems sort of much a little quicker if you have this thing. There's some patterns there that make it a little easy to memorize. So there's a very important fact. We call these things in math, we call them theorems. So this is important, what we'll call theorem. So so the binomial distribution has mean. Its mean is very simple. It's just mu equals n times p. And variance is quite easy to remember too. It's n times p times 1 minus p. Now you can actually, if you wanted and you were clever with some math skills, you can actually derive these formulas. It might be a little bit above the level of math. And I don't mean that you're not capable of doing it. What I mean is most students in a class of this level, you don't have as much experience with making certain types of mathematical arguments. And so deriving the mean formula and deriving the variance is probably a little bit above your pay grade at this point. Not that you couldn't do it, but it would be quite difficult. But these are nice shortcuts that you can use to answer questions. So I would encourage you to try to keep that in mind. So let's look at an example quickly to see how these can sort of be used. So a die is rolled, let's say 500 times. Determine the mean of the number of sixes that will be rolled. So again, another way to think about this is if you roll a dice 500 times, how many sixes do you expect? Well, you could go ahead and calculate it the long way using the definition, or you can just apply this formula. So it's just a quick little multiplication. So the probability of a 6 equals 1/6. So that's your success. And there are n equals 500 trials. You're going to do it 500 times. And so it's pretty easy to see then your mean is 500 times 1/6. which is 250 over 3, which is approximately 83.33. So essentially what we're saying is you would expect roughly 83 sixes if you rolled it 500 times. Or another way to say that, if you did this experiment a bunch of times and you averaged it out, you would have on average 83, roughly 83 sixes. All right. Any questions about this? Okay, so there's two other distributions that are worth knowing. The first one is what we call the geometric distribution. And the second one is called the Poisson distribution. Poisson. So what do these guys look like? Well, the geometric distribution is quite useful. So maybe we can motivate it through one of the problems we've been doing. So let's do that. So here's how we might want to motivate it. So to motivate, consider our old game that we had discussed a few times. Consider flipping a coin until heads appears. So let's remind ourselves what the sample space looks like here. So the sample space is an infinite list, really, because we have to think about it. How can the game end? Well, you can get ahead on the first try, then it's over. But if you don't get ahead on the first try, you might get it on the second try, or you might get it on the third try, or you might get it on the fourth try, etc. So this is sort of the pattern of the sample space, and it's infinite. So the way to think about this is, suppose the question was, how long do we expect this game to last? Or what's the probability it ends on the fourth time? Well, we can analyze that, because if you take, for example, if you look at this case, and we think about each one of these being a binomial, then you have failure, 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 success. So here, if it ends on the fourth try, you have 3 failures, and then you have a success. So if you think of it that way, then you might say the probability that this occurs, the probability of T heads would be, well, you have failure, failure, failure. So that's 1 minus P to the third power, because there's 3 failures. And then it's times P, because that's the probability of success. So notice I'm looking at a general case here. I'm not even suggesting these coins are fair. I'm just suggesting a heads has probability P, and then a tails, which is the failure, has probability of 1 minus P. So you don't even need to think of this in terms of coins. I might say, okay, let's roll a dice until we get a 6. And then your probabilities aren't just going to be 1/2. It's going to be slightly different. So what we say then is we call the probability that a random variable equals k is given by this formula. A geometric distribution. So what this way you can interpret this in English is, this says, or not says, but maybe this tells us the probability of success on the kth trial. So if you go back to that one test question we had, we asked sort of a similar question. We said, how long do we expect the game to last? And as some of you pointed out, it was interesting because some of you got the answer. But it's probably not clear to most. Well, I shouldn't say that. Maybe some of you understand it. We're going to show you what it is in a second. So turns out, here's a fact. The mean for this distribution is 1/p. And this should not, it's actually very, I caution to say obvious, but imagine a coin whose probability of heads, if it's fair, is 1/2. Well, basically this is asking how many times do we expect to play the game until, how many flips would we expect until we get a head? Well, if we expect to get ahead 1 out of 2 times, then it shouldn't surprise us that the game we would expect then to last on average 2 tosses. So to see why this is true requires a little advanced math, and some of you might actually know it, but we're not going to go through it because I don't want to scare you. But to see why this is true, you need some calculus. In particular, you need some knowledge of what's called a geometric series. And we're not going to go into that. If you do know what that means, then you can Google it and look it up. But okay. Does anybody have a question, comment? So let's just look at that example in the context that we're talking about. So example, how long do we expect the game to last if P equals 1/2? Well, that's a fair coin. Well, since mu equals 1/P would be 2, on average, we'd expect the games to last 2 tosses. Or 2 flips. Maybe I should be more careful with my English. How long do we expect the game to last if the coin is fair? Okay, so now let me reiterate, this doesn't just have to apply to a coin toss game. We can imagine lots of scenarios where this might be useful. Maybe we're trying to figure out how long, until a certain medicine we have success. How many patients, how many customers before one of them buys something. So there's lots of different ways that you might be able to make use of this distribution to get information. Does anybody have a question? Comments, concern? All right, so the geometric distribution is sort of useful for asking how many fail, or when are we going to have a success? How many times must we do a trial before we get our first success? Whatever your success must be. Another question that is similar but not identical is something like this. So the Poisson distribution helps model, or helps to model or explain the number of times an event occurs so for example, over an interval of time. Or maybe space. So what do I mean by over an interval of time? Well, maybe you own a department store, or maybe you're Amazon, and you might want to know how many times do I expect to sell something over this time period versus, you can imagine maybe it's different hours of the day are more popular than others. Maybe different times of year. Obviously, if you are a maker of swimsuits, depending on what part of the world you're on, you're probably going to have times a year where you sell many more swimsuits than other times of year. So if, I guess there's other examples I can give you, and it's, you guys aren't knuckleheads. You can easily Google the Poisson distribution and applications, and you can maybe maybe you read about places where this is of use or can be of use. One of the standard examples that I've seen to help motivate this is imagine, you have a room, and maybe I have 30, I come in here and I get like 30 1-gallon buckets, and I put them in the middle of the room, and then I say I'm going to go get like, I don't know, maybe I go get 1,000 golf balls, and I just throw all the golf balls in the air, randomly. And then I ask myself, what happens to these golf balls? How many buckets, or how many, if I just pick a random bucket, how many golf balls were in that bucket? And so it turns out, if you do some math, and again, I don't want to go into the details because it's probably not the most important thing right now, but the applications are at least a little more of use. Is the following. So here we go. So once again, we'll have probability of some random variable. And we want to know when it takes on some value, which we'll call K, as we've been doing. And this turns out to be equal to some number raised to the power K divided by K factorial times some other number raised to this negative lambda. So this looks scary. So let's explain some of these things that you might be unfamiliar with. So we call this Greek letter lambda a parameter. E is the constant. Some of you should have all at least seen this once or twice in your life, perhaps in a college algebra course. It's very famous, and it shows up in all types of different places. And it is approximately 2.718. And it's actually an irrational number that goes on forever and ever and ever. So some interesting things about this, it has mean and variance are the same. And so we can write that down. So the mean of this creature, and again, this takes some higher math, so we don't care about it, but it's nice to know so you can answer simple questions. The mean happens to be lambda, and that's also the variance. All right, so let's do an example that uses this distribution. Oh, does anybody have anything they want to say? You don't have to. You guys are quiet. I assume you're all sleeping.
I'm just eating a salad.
What's that? You're eating salad? That's good. A salad. By the way, I guess it's worth noting. So we should say this on the previous page. I failed to mention it, so I'll put it here in red because it's important. So if you come up here, we talk about modeling the number of times an event occurs. So that because that's what we're trying to explain or model or document, it seems that it's important that this, this distribution encompasses that. And so for that reason, we think of lambda is sort of the mean of the occurrences over a given unit. So maybe it's an hour, maybe it's an area, maybe it's a volume, depending on what you're studying. So what that means is you can't really do anything unless this number is given. So here's a sort of a standard example, and hopefully will make some sense to you. So I don't know if it will. So an emergency room. Sees 3 patients on average per hour. So for any given hour, determine the following probabilities. First, let's say at most 3 patients. At least 3 patients. Or let's say about 7 or more patients. So I guess I should spell 7 or more correctly. So we need to figure out how to use this formula. So what is this formula telling us, or I shouldn't say telling us, but how can we interpret it? That the probability that a random variable is equal to a specific value is given by this. Okay, so first off, we need to interpret how this works. So let's think about this. So note that P x equals K is the probability of K patients. So at most 3, what does that mean? Well, that means by our axioms that's the probability that we get 0 plus the probability that we get 1 plus the probability that we get 2 plus the probability that there are 3 patients. Now, this is sort of a pain, but we have to do it. If you go back to your formula, the formula is lambda to the k, k factorial e to the negative lambda. So here, what is our lambda? Our lambda is 3, so this means 3 to the k. I wrote that wrong. Erase. So this would be 3 to the 0 over 0 factorial times e to the negative 3. And this would be plus 3 to the power 1 over 1 factorial times e to the negative 3. Plus 3 squared over 2 factorial times e to the negative 3. Plus 3 cubed over 3 factorial times e to the negative 3. So what's nice about this is I have this e to the negative 3 everywhere. So, and again, well, I guess we can go slow. This is e to the negative 3 plus 3e to the negative 3 plus 9/2 e to the negative 3 plus, so 3 cubed is 27, and then 3 factorial is 6. So what you end up getting is 9/2 e to the negative 3. Now we have to double check that, but it seems to be correct. So again, I'm doing some arithmetic here. Anything raised to the power 0 is 1, and 0 factorial is 1, so I get this. 3 to the 1 is 3. 3 squared is 9, so I get 9 over 2. 3 cubed is the same as 3 squared times 3, so one of those 3's will cancel with the guy down here, so I get 9 over 2. And provided I didn't make any errors, what we can do is, one way to do this without a calculator right away is pull out e to the negative 3, and I'm left with 1 plus 3 plus 9/2 plus 9/2, which is 9. So this is 13 e to the negative 3, which we would need a calculator to sort of go after. By the way, you know, most calculators have e on it, so it's not hard to get to the bottom of that. So if I do this, I get approximately 0.6472. Or if you want, 64%.
I have a question.
Yes.
To figure out each probability, the likelihood, would you just plug in the 3 solutions for X and then just work them out?
Yeah, you talking about, well, let me make sure I'm understanding your question correctly. You don't want to say 3 solutions for X. You want to say 3 values of X. But there's really 4, right? Because we have 0. There's the chance that there's no patients. There's the chance that there's 1 patient. There's a chance that there's 2. And then there's a chance that there's 3. So for each one of these, I am taking this number here or this number here, and I'm putting it where K is. So you have to, in order to do this properly, you have to know how this formula works. So I'm going to first let K be 0. then I'm going to let K be 1, then I'm going to let K be 2, and then finally 3. And if I do that properly, I get these 4 values. Now, you could have just went and plugged them into a calculator right away. You'll get the same number, but just being my own personal philosophy is I like to do it by hand as far as I can. I don't know if I answered your question, but what?
Yeah, you answered my question.
Yeah, what I hope you'll again, if you want, let me write this in red just so it's clear. What this is equal to is this is 3 to the K over K factorial times e to the negative lambda. But in this problem, lambda is 3. You're told that in the problem, so that's why you get e to the negative 3. So for each one of these, say that again.
I got another question too. Yeah. The 3 to the 3rd power, wouldn't that be 27 though?
It is, but this is over 3 factorial. So that's a good question, but think about this. So I'm thinking of 3 cubed. I'm thinking of this as 9 times 3. That's 27. Do you agree?
Yeah.
But then downstairs you have 3 factorial, which is 6. So this is 3 factorial, so that's 6. So I have this over 6. And so if I allow this 3 and this 6, it cancels that 3. That's how I get 9/2. So 27 over 6 is 9/2. Is another way of saying that. Does that answer your question? Yay, nay?
Yeah.
All right, so very good. So again, let me digress for a second. I want to be fair with you guys. This is not the easiest. I mean, I know for most students in this class, I mean, I don't want to paint you all with the same broad brush, but a lot of you already told me since day one you don't like math, you blah 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 and all that. For those who haven't had lots of exposure to the language of mathematics, this can look very overwhelming, and I understand that. But I promise, if you give it effort, it's not that, conceptually, it's not that bad once you give it. I'm not asking you to, we're not teaching you how to split atoms here. This is not quantum physics. This is, for all intents and purposes, it's arithmetic. The problem that we have, though, from your end is that it just looks overwhelmingly chaotic. It looks scary because we're using symbols you're not familiar with, and you just have limited exposure. And so that's part of the reason, in a class like this, one of the things I find is often students, you guys, I don't want to say you give up, right? You don't like wave the white flag. But I think a lot of times just the look of this, the way it's presented is overwhelming to lots of students. And then you kind of just say you're not even going to give it an effort because it just seems so, overwhelmingly difficult. When actually, it's not so much conceptually and mathematically difficult. It's just that the language that it's written in is overwhelming. All these exponents in this, these equal signs. It's if you take the time to understand what this notation means, it makes it a lot easier to follow the rest of the way. But again, I'm not going to pretend it's easy. I once sat in a class like this and was asked to learn this stuff. And like many of you, I was overwhelmed and lost. So, like I always joke, I have sympathy and empathy for you guys. I feel bad and I know the feeling. So, but I do think, I do believe, I should say, that if you put the effort in, you can make sense of it. Okay. Let's do the next one. So the next question, this was part 1, by the way. So I asked you to do 3 things. And then the next one is I asked to do what? I said at least 3, right? So at least 3, yeah, I guess we should, at least 3 means, oh boy, 3, 4, 5, forever and ever. Well, that's impossible unless we use our axioms. So instead, use the axioms. What do the axioms mean? Well, the probability that there's at least. So I guess the proper way of writing this is that the random variable is no smaller than 3. So the proper way of doing this is that you say the random variable is greater than or equal to 3. So the quickest way, and in fact, in this problem, really the only way to do it is say 1 minus the probability that x is less than 3, the complement. And so we already figured most of that out. That would be the probability that x is equal to 0 plus the probability that x is equal to 1 plus the probability that x is equal to 2. Now, if you look at what we did in the previous problem, we found those. Those are right here. It's the first 3 pieces of this. So I could just do them again, or I could say, oh, that's right, we already have this. So this would be e to the negative 3 plus, the first one was e to the negative 3 plus 3e to the negative 3 plus 9/2 e to the negative 3. And to save time, what I would do is I would just go to a calculator and compute this. So that's what I'm going to do. And by the way, if you have any issues with knowing how to do this with a calculator, just let me know. You can do it privately if need be. And so if you do this correctly, you get approximately 0.5768 or 57.68%. So again, there's a lot of computation happening here. I highly encourage that you try to work through these things. Now, the last one is really a pain. So what I'll probably do is just set it up and say, if you want to suffer through it, suffer through it. Because the last one I said 7 or more. So how would we write that? Well, yikes. I mean, that looks like an insanity. Because for this part, once again, you'd want to know when is the random variable, the number of patients, going to be 7 or more. So in the language of math, that's x greater than or equal to 7. Well, that's going to be 1 minus the probability that x is less than 7. And so in order to compute this, you're going to have to do all of these. The scenario that it's equal to 0, plus the scenario that it's equal to 1, and then plus the probability all the way up to you get 6, which seems very, very tedious. But of course, as I suggested yesterday, there are lots and lots of places you can get Poisson calculators for free. The internet will do it. I'm sure there's apps you can download. So maybe for, again, this is something that I'm not going to go through it, but maybe you can for your own practice. I think I would imagine if you probably just Googled Poisson calculator, you'd find one. Yeah. I just found one. I literally Googled Poisson calculator and I found one. So my advice would be for you to go out and try to find one, see what you can get. And by the way, using a calculator, we can compute this. So I guess I'll delete this. And then maybe you can figure out or see if you can get the same answer. So this becomes 0.03350, or of course, 3.35%. Any questions, comments? By the way, let me just share with you what I did. I literally, here's what I did. So I literally went Poisson calculator. And the first hit is this thing. And so if you want to answer the first two questions, what are we trying to figure out? We were doing what happens when it's 3 and our average was 3. And so if I calculate, you'll see we get two answers. Less than or equal to 3, this is what we got, 0.64, and greater than or equal to 3.57. So you'll notice that these two numbers matched what we got when we did it by hand. Now, if I switch this, instead of doing 3, I wanted to do greater than or equal to 7. If I rerun it, you'll notice that down here I get 0.33 or 0.335. So that's how I got my number. Anybody have any questions or comments?
I have a question.
Yes.
Who's Tom Hardy?
Yeah, that's funny. So we were talking in the last class. Let me go back about I watched this movie on Monday night, and I couldn't remember who was in it. I was like, it's Tom, and I was like, he's a famous actor, and we couldn't remember. So then we Googled, and then someone remembered that it was Tom Hardy, and we were talking about this show that he's on called Peaky Blinders. I don't know if you've
Such a good show.
Yeah. So we were joking how when you watch that show, though, I have to like watch it with subtitles because I can't understand them. They have these super thick, like British or Irish accents, right? It's like really hard to follow along. Anyhow, that's why this was up. Look how many tabs they're commenting on this. I got tabs galore. Wonder, yeah, fantasy footballs up here. We got all kinds of programming stuff. You know how to do all kinds of fun things I'm learning. We're simulating poker hands. This is all kinds of fun. What is this? I'm buying things on, oh, here's a good book from you guys can study. All kinds of fun stuff. All right. Does anybody have a question about this? So look, these are some difficult, challenging topics. This geometric distribution and this Poisson distribution. You know, I caution you not to stress too much over it, but I think it's worth your while to at least be exposed to them. What's cool is it turns out the Poisson distribution is actually related to the binomial distribution. So I don't know. Figured it would be something that would be a good idea for me to talk about. By the way, all these distributions we talked about, these are all examples of what we call discrete distributions. So what we're going to start next week is what's called the most famous of them all, the normal distribution. Also known as the bell curve. So this is an example of what we call continuous distribution. So we'll talk about that in some detail and how it's related to the binomial distribution and all kinds of stuff. We'll do that on Monday. So it's probably a good place to stop. I'm happy to answer any questions you guys might have. And if you have questions, ask. If not, I will talk to you guys on Monday. By the way, look out for, I'll give you a nice short homework this time. How's that sound? And probably another quiz. And by the way, I don't find these quizzes to be difficult. If you do, let me know. But the way I'm thinking about it is I'm giving you guys, they're very low stakes. They're not difficult questions. And so if you think I'm being unfair with them, please let me know, and I will. Well, you can let me know when you do that writing assignment. So anyhow, if you guys don't have questions, I say thank you very much, and we will see you next week. Be
Can I
safe.
ask what your picture behind you means, or if it's just a random picture?
Oh, behind me. It's not a random picture. That's the Woo